Morning, everyone. So yesterday we started looking at solution chemistry. We're going to focus on solutions that are made from dissolving solids into liquids. We introduced our main conversion factor, which is called concentration. We looked at a few different units. It could be gram per liter, measuring masses. If you happen to know what the chemical is and you have the periodic table, you can use molar mass to convert to a more useful mole per liter. We saw at the end drawing that summary diagram there. Once we get back to moles, we're happy to convert over to number of particles and volume of gas. We can navigate around that diagram. We also did parts per million for a little bit. It's just setting up a ratio based on really tiny amounts of chemical. I need to scale it up by some million. Parts per billion would scale it up by a billion to try to make sense of really tiny numbers. So I'm just going to rehash for you that summary diagram, and then we'll finish up some of the terminology in solution chemistry, work our way to a dilution calculation, and towards mixing in this lesson here. So again, for good practice here, just start drawing this diagram multiple times here, maybe once a day, so you can fully internalize this. We're starting to really see the mole is the middle of our diagram. We can convert, well, the mole is basically like a box. If I want to find out how many particles here, we use Avogadro's number, which is 1 mole is actually 6.02 times 10 to the 23. Just like dozen here, the dozen refers to the number. It doesn't actually qualify the object. Same thing here. 1 mole was actually defined as Avogadro number of carbon. I'm now going to borrow that number for every other element. A mole of magnesium would be an Avogadro number of magnesium. A mole of people would be that many people, right? So that's numbers to moles. If I happen to know what the chemical is, I can go to a bubble of mass. In this case here, we actually have going to mass, we need to use a conversion called molar mass. And molar mass here is going to be from the periodic table, the units that we're going to associate gram per mole. Usually it's best to say the units are actually, there's no units because it's relative to carbon being just 12. But for us, because we want to cancel out units, so I'm going to include gram per mole. Earlier we had done volume bubble. Again, I mentioned there's 2 restrictions on this volume bubble here. The first restriction is probably more important for us here is it is a gas. You can assume that we're at standards. If it's nicely worded, it'll also remind you we're at standard temperature pressure. In tomorrow's lesson, we'll come back and we'll actually derive how did they get this number. Again, this conversion here itself is called molar volume. Molar volume was 1 mole of any gas. It just depends on temperature pressure. So if I'm at my reference, this is actually 22.7 decimeter cube. And lastly, from yesterday for our solution chemistry here, we'll notice we have a totally new bubble here. This is volume, but this is talking about dissolving solids into liquids, and this time it really depends on your concentration. It depends on how concentrated or dilute your sample is. Once you get back to mole, you're more than welcome to freely move around the diagram. While I have this diagram on the board for you here, we've been using density as a conversion factor. Density is also a volume bubble. We're not going to do it too much. I'm just going to draw it really small in the corner here. You can have volume of a pure liquid like water. How do you get from volume like a liter to grams? Density is actually this conversion here. We saw density help us find molecular mass in our empirical formula lesson, but that is sort of attached there. We usually just say, oh yeah, grams is mils, but remember that when there is just water, if you're using oil, if you're using other chemicals here, the density might actually be different. So just for completeness sake here, I'm just including that here. We're not really going to worry too much about that last conversion. I'm going to give you one practice question here with this. This is we practiced with solutions from yesterday. Let's do here. What volume of 0.96 molar cobalt 2 nitrate solution can be made from 720, that's actually quite a lot. Let's do 72 grams. All right. So we have that question worded out here. We're going to see if we can place ourselves on this table here. We're interested in finding a volume. Oh no, I actually have these 2 main volume bubbles here. Am I looking at volume of gas or volume of solution? Well, they're telling me it's going to be solution. They didn't actually need to write that in words. If you see that there's a capital M, that capital M means moles per liter. It's molar. So that one there already tells you the solution. So I'm interested in getting to this bubble, not the gas bubble here. the concentration is 0.96, that means my solution, for every given liter, there's 0.96. I don't happen to know what the volume is. That's what I'm actually interested in calculating. But what they actually give me, sort of in reverse, they sort of give me, well, with my kitchen scale, I measure 72 grams worth of material. Let's just do this picture. If I draw a solution, usually this is how you make a solution. You put in your powder. So we have 72 grams. This is our cobalt nitrate. So CONO3, 2 like that. I'm going to start adding in water. At first, when there's very little bits of water here, the concentration here will be really, really intense, really, really strong, probably higher than the 0.96. I'm going to keep adding water until, with these swimmers swimming in my actual water, the concentration is actually 0.96 molar. If I happen to add too much water, well, I don't have enough swimmers to actually make the concentration high enough to be 0.96. I would have diluted the sample. I'd be actually lower than 0.96. So the question is, what is this special volume, the exact volume of water that I can add, assuming you use a stir stick and mix out the powder, that the concentration remains? Maybe the lab called for 0.96 molar. So let's just try it out here. You're going to try to get some practice doing it all in one long row. If you're practicing and you just want to do one step at a time, you can. Just make sure you don't do any preliminary rounding. So in this case here, we're interested here. My final unit is going to be question mark liters. My solution here is cobalt nitrate. Again, these solution questions here are always a little bit more challenging to start off with because they always give you two numbers. If you look back at all the conversions so far with molar volume, Avogadro's number, they only had one number. It was like, I have this number of particles, how many moles? I have this number of moles, how's the volume of gas? In this case here for solution chemistry, they always need to give you two numbers. In this case from the diagram, we see why that is. One of the numbers will place us on the diagram. I would start off with the number that's easier to work with. In this case here, 72 grams is easier to work with because that puts me directly, okay, I'm at this mass bubble. I want to traverse over here. I want to eventually make it over to volume. And what they're actually giving you for the other number here is concentration. And concentration actually is my conversion factor. That's actually going to help me do this second fraction. So that's why we needed those two fractions there. Let's still set this up here. We were interested in going from 72 grams. From my summary diagram here first, I'm going to get rid of grams and go to moles. So grams on bottom, moles on top. I'll need molar mass. And then what I'm going to do is I'm going to go from moles over to volume. So I'm going to get rid of the moles and eventually go to liters. All right, so at least I've set up my units. Gram cancels gram, mole cancels mole. So let's go to our periodic table here. Let's add up cobalt nitrate. Cobalt is 58.93. I can add 2 times. I can put in brackets here for nitrate. Double check my numbers. 14.01 for N plus 3 times 16. Then there's cobalt nitrate. I'm getting 182.95. Right. My periodic table had 2 decimal places. When you add up numbers have 2 decimal places, the sig figs are going to be 2 decimal places. That's the number of moles for a given liter. And now, when I'm tempted to use 22.7, oh, 1 mole is always 22.7, right? Remember, that was only for gas. That would actually knock you down this way. Well, we're not actually going that way. We're actually going down the solution pathway, even though we are still trying to do the same conversion, moles to liter. This time, I'm actually going to use the other number. This says 0.96 with the mole. There should be a 1 with the liter. This is the one conversion that the 1 actually goes with the liter. It says 1 liter is a convenient measure. So if there's a 1 by a liter, I actually have 0.96. Based on where the units have to go, I know to divide these two numbers. So let's go 72, divide this 182.95, divided by 0.96. And I find out the amount of liters I can make is 0.4099, so let's make it 410 like that. The unit will be 4.410 liters, or you can write that out here, 410 milliliters. Do keep an eye on your sig figs here. Actually, this is 2 sig figs, so I'm just going to leave that. Oh, perfect, 410. All right. Looking back at our summary diagram, I just mentioned here, yes, concentration became our new conversion factor. Concentration here was to get to moles to liter. You'll notice that the 1 sticks to the liter. Let's look at the other conversions. In this case here, Avogadro's, 1 sticks with the moles. For periodic table, it's per 1 mole. Molar volume, it's 1 with the moles here. Solution 1 is the only one that actually is. Let's put a 1 by the liter instead, and let's figure out how many moles I've actually dissolved. So just look out for that. That's a nice practice of our solution chemistry. I want to just rehash with you some of the vocabulary in this section, and then we're going to look at one last calculation for solutions. Let's focus on this term here, solubility. The solubility of something here measures its ability to dissolve, its ability to break up, its ability for the solvent to actually rip apart the bonds. When we were doing our reaction section, we had a chart of solubilities. If you remember, this is the chart. We started looking at the negative ion first. We had the positive ion that I mixed and matched it with, and then the sort of conclusion was over here, whether it's soluble or not soluble. If you look back at the chart here, I'm going to just qualify for you again. The term soluble means dissolve greater than 0.1 mole per liter. We now understand this number a little bit better. So this one says, pretend I have 1 liter worth of liquid. As you drop in your powder, if you manage to dissolve enough powder that at least you can get 0.1 moles in this 1 liter worth of solution, I'm going to call you soluble. Even if you dissolve only 0.09, I'm not going to call you soluble. So I'm setting an arbitrary reference. This is basically 0.1 molar. They also say at 25 degrees. Solubility is also temperature dependent here. Particles tend to move a little bit faster. They, in general, dissolve things better when they're hotter. There are some strange chemicals that actually get less soluble when you heat it. Strange enough. But there we go. That's what it means to be soluble. We have that criterion. It has to be more than 0.1 moles per liter, and the temperature is 25 degrees. So therefore, when you mix and match your combinations, if you had the phrase here soluble, we would use the terminology aqueous, it breaks up. If it was rather low soluble, or even you can say insoluble, everything dissolves to a certain extent. It's just, this is actually a fairly low limit here. If you dissolve even less than that, practically we can say you don't dissolve. So soluble, this one here dissolves well. That's why we said it's aqueous. For low soluble, we're going to put solid. In this case here, it's very poor at dissolves. Remember, this table here in general had the most soluble things at top. We're not given this chart here on the IB data booklet. There's just some common trends I would memorize. Things that are always soluble. So we're looking really high up on the top here. We're looking at salts made from alkali ions, H+, ammonium. Those salts are always soluble. For the anions here, nitrates are always soluble. I would definitely memorize these ones here. So alkalis with any negatives, or this anion here with any positive, those ones that are always soluble. Don't even bother checking the solubility chart here. These ones dissolve really, really well. But as you work your way downwards, we're going to get less and less soluble. We do want to actually mix and match the charges, test each compound one by one. So let's have another look in detail here. When we say these alkali salts here are soluble, what actually happens to them when you actually drop into water? So let's take our friend here, sodium chloride. Sodium chloride here starts off as an ionic solid, right? But I thought you said alkalis or salts are always soluble. Well, I haven't tossed in water just yet. So this is just plain old table salt. I know it would dissolve in water, but I haven't tossed it in yet. The experiment is I'm going to then toss this into a container of water. Water is assumed as my solvent. Water is assumed as my background. What I want to study here is I want to figure out what does water do to this ionic compound. As an ionic compound here, we know it's made out of Na pluses. Every Na plus should have one counterbalancing Cl minus. But because the charges are greedy here, they're going to actually surround themselves with as many counterbalancing ions as possible. So the Na is actually going to surround itself with many, many Cl minuses. The Cl minuses will surround themselves with many Na pluses. At least on average, for every one Na, there's one Cl. That's called the formula unit again. It's almost like an empirical formula inside this lattice structure. We want to know what water is going to do to this. And what's going to happen here is when you actually drop this in, it almost looks like a decomposition. Water is going to come break up some bonds. What water is going to do is water is just actually going to come in and actually separate this lattice. It's actually going to pry apart the sodium from the Cl. What's going to end up with is you're going to end up having just many Na pluses swimming by themselves and just Cl minuses swimming by itself. So water has separated the positive from the negative. I can write that as an equation here. When I drop NaCl here into water, sometimes we put the reacting conditions above the arrow. We've seen using the triangle for heat here. What's happened here is a dissociation. It's a new reaction. Earlier when we said decomposition, I would have said, well, chunks of sodium and just chlorine gas forms. Well, we know we don't poison ourselves every time we drop salt into water. In this case here, water just separates the positive from negative. So the positive is the Na. It's showing off as positive now. And the Cl minus is going to be the negative. It's going to be Cl negative like that. This is actually a new reaction here. I'm going to give it a new name because it's not quite a decomposition. We're going to call this instead a dissociation. When things dissociate, I'm saying things fall apart. So break apart. We break apart into the positive, we break apart into the negative. This reaction here is also sometimes referred to as an ionization. I don't like that definition too much, but in this case here, ionization means you end up making the ions. In this case here, I want to emphasize, you'll notice the ions were actually there to begin with. Na was always plus, Cl was always negative. That electron transfer guaranteed that. It's just that, remember, we had worked out the ratio, charges in general are unstable. That's why NaCl had overall no charge. But now that water has come in and actually separated cation from anion, now all we're going to do is we're going to show off all our charges. We're going to just reveal our charges. I prefer that language rather than becomes charged. In some sense, you're right, it does become charged. It goes from a 0 as a solid to suddenly becoming charged, but I want to show you that, hey, even in the solid state here, the Na was plus, it's just showing off the Na plus charge over there. So that's called a dissociation or ionization. In this case here, because it is not a decomposition, you'll realize here this is actually not a diatomic. But wait a second, I thought whenever chlorine was by itself, it's unstable. In fact, in this case, you're totally right. The Na plus and Cl minus are unstable. Charges are unstable. But what is water going to do to actually help to stabilize them? We're going to do a little bit of background here. We'll come back to this a little bit more in chapter 3. Water is what we actually know to be a polar molecule. A polar molecule has two poles, has two ends to the molecule. Water has the two H's, it's actually covalently bonded to an H. We know a covalent bond actually refers to electron sharing. So oxygen doesn't tug of war hard enough to actually completely steal hydrogen's electron. However, oxygen here is more of a bully in the picture. Oxygen, even though it's supposed to be sharing electrons with the hydrogen, the oxygen here is actually more electronegative. It's actually more of a bully, and he actually hogs the electron density. He hogs the negative charge to himself. What that's going to do is it's going to cause the negative side, this end of the water molecule, to be kind of negative. I'm going to use the lowercase delta as like a squiggly d. This one here says a partial negative because the negatives spend a little bit more time with the oxygens and the hydrogens, whereas hydrogens they're still sharing, but they happen to sort of lose out on some of the electron density here. What we get on the other end here is actually a partial positive. That's why we can call this here a polar molecule. This water molecule actually has two ends. So back to the question, careful that in the dissociation, this one here is not diatomic. What's allowing it to be stable? What's allowing it, if you look at the Bohr model, it actually does have a full shell. That's actually one thing in its favor. But what's actually helping to stabilize these charges is actually the background of water. So if you imagine here, let's take a look at a zoomed in picture of the water. Let's zoom in at just one single Na+. Pluses should not be stable. When I have a bunch of waters come around though, waters say, oh, positive here is unstable. Water's going to prefer to point its negative end towards the Na+. So waters are going to very quickly flock to the Na+. If water can actually surround this Na+, it can actually help to stabilize this Na+. Water overall is a neutral molecule, so water cannot get rid of the positive charge. But the analogy here is, imagine this positive here is unstable. It's like a hot potato. The Na+ really has a hard time holding on to it. Once water actually helps surround it, water, we're going to see in chapter 3, actually complexes with Na. It's almost like Na becomes suddenly a much larger molecule. The overall hot potato is still there, but seeing as I become a much larger complex, I can spread out my charge a little bit more. It's like I can pass this hot potato around. I don't have to be the sole ion that's actually holding onto this charge here. In exactly the same way here, the Cl minus. Cl minus here, Cl alone shouldn't be stable, but with that negative charge, water will flock to it here, and it's going to point its positive end. The actual number of waters is going to depend on how much, sort of the proportions, what's the molarity of the solution, what's the molarity of the chemicals, but pretty much we're just generalizing here, and we're saying water is going to stabilize by pointing its opposite charge to stabilize that negative charge. So let's just write this down in words here. Water, I'm actually going to give you the full name here. Water acts as a ligand. We're going to see that term a lot more in chapter 3. Ligand is a sort of a group of species that actually do this particular behavior. So water acts as the ligand and stabilizes both ions by surrounding. Or chemically, we're going to talk about it's by making a complex ion by complexing with the ion. Right? So water overall neutral, it can't actually get rid of the positive, get rid of the hot potato, but at least by forming a much larger molecule, it can actually work towards actually spreading out that charge a little bit. That's just a little bit of the background here. That's what actually makes water a really good solvent. Most ionic compounds will end up leaving ions in solution, and because water is always polar, water can always twist itself around so that it can actually stabilize the counterbalance charge. Let's do one more practice here with just writing a dissociation reaction. Let's take the salt here, NH42SO4. You should be able to name that. Just like we did in the decomposition, when you're tempted to say, oh, we just have one chemical falling apart, I'm going to get N, H, S, and O, it probably won't decompose into so many things. In this case here, what I want to show you, this NH42SO4 itself is a lattice, sure. NH4 here is ammonium. Inside this structure here, somehow bonded, I have two NH4s per SO4. We mentioned previously here, this is a compound that has both ionic bonding. So the positive of the NH4 plus is attracted to the negative to the sulfate. But we'll notice internally, let's say the sulfate here, that sulfate is actually bonded covalently. It's non-metal, non-metal. So this is a molecule that has both ionic and covalent bonding. We said water has no trouble breaking apart the cations and anions because the leftover charges water can stabilize. Water is not strong enough to actually break up the polyatomic, break up these bonds. So just as a general rule here, polyatomics, those ions, polyatomic ions stay together during a dissociation reaction. So the ions that we get, usually we'll get one thing positive, one thing negative. The positive, this thing here is ammonium, so NH4 plus. The negative is actually sulfate, SO4 minus 2. We still need to balance it, however, in this ratio here, every time I break up one of these formula units, like an empirical formula, I actually get two ammoniums and only one sulfate ion. Right? So water is good enough to break apart the ionic bond. Water cannot break the covalent bond because the covalent bond is stronger. I want to introduce to you one other terminology here, and then we'll get back to some calculations. Let's take NaCl. Right? So NaCl here was table salt. We had talked about here, table salt here should actually be able to dissolve. This one here on the table is soluble. As long as it's out here, it can be solid, but the second they drop into water, the NaCl is going to break up. It's going to break up to form Na plus ions, Cl minus ions. It's just going to completely break apart. What's going to happen here is you can eventually, I only have so much water, you can toss in more, it's going to break up more. You can toss in more, it's going to break up more. Toss in more, break up more. In fact, because something is soluble, we can have way more dissolved in here than that 0.1 mole per liter. Eventually, though, you're going to hit a point where as you toss in some more, it looks like that table salt here just actually stabilizes and actually settles out here on the bottom. In that situation here, we're going to refer to this here as a saturated solution. That word there, saturated, means it's been packed full. A saturated solution contains the maximum amount of dissolved solute. I only had so much water. I only had so many places that the solids can actually dissolve into for the liquid. If you totally saturate, you totally fill up all those pores and totally fill up all those holes, I can no longer dissolve anymore. That's now become saturated. Even though outwardly, we would say macroscopic properties are constant. Macroscopically constant. We're going to learn next year. In fact, it's actually not constant. This, what we are going to refer to as an equilibrium. This equilibrium here, in fact, even though it looks like the powder is just sitting there, the powder is constantly dissolving. Why is it that it looks like the powder is just sitting there? Well, as the dissolving still happens, there are other particles that actually crystallize out at exactly the same rate. As long as they do those transfers at exactly the same time, macroscopically we stay constant, even though microscopically the reactions still happen. Microscopically, reactions continue. Right? Imagine a hockey game analogy. Let's say whenever we do a line change, as long as 3 players go off and 3 players come on, we'll always have the same number of players on the ice. So that's what we have for an equilibrium. That's what we get for soluble. It takes a lot before this to happen. Let's contrast this here with the salt that's not very soluble. So let's contrast it with AgCl. If you check your solubility chart here, this one here is labeled as low soluble. This one here doesn't dissolve very well. So again, outside here it can be solid. You're going to take some of this silver chloride and you're just going to drop it in. Now, to be sure, if you drop in just a smidgen of AgCl, you might manage to actually dissolve the AgCl. it's just way less than that arbitrary 0.1 molar limit that I put in. It's not going to take much more. Maybe drop in the next X there, and already it's saturated. Already the HCl can't dissolve. Again, realistically, it is dissolving. It's coming out at the same rate. That's why the solid doesn't look like it's doing anything. What I want to show you in this example is, in both cases, we have hit saturation. In both cases, we have hit a mixture which has dissolved the maximum amount of solid. It can't handle dissolving anymore. The only difference, however, is how much until this happened. Something that was soluble, you toss in a ton before this saturates. Something that's low soluble, you drop it in, oh, it already doesn't dissolve, it means it's already saturated. And even if things are fully dissolved in here, you can't do this sort of wishful thinking here. Well, if I see the solid on the bottom, what if I just skim the liquid on the top? Well, because the reactions are continuing to occur, the liquid, even though I may not be able to see it once it's mixed up like that, it's going to be very, very salty. It can't just do like a simple, oh, let's just do a filtration technique. Let's just separate off the solid and it won't be salty anymore. Well, no, there are actually the maximum salt. It's going to be the most salty if I can see there's leftover solid at the bottom. So the difference between things that are soluble and low soluble is how much until saturation. This one here doesn't take much. The NaCl, it takes a lot. We're going to always assume in our questions upcoming here, we're going to assume we're very far away from the saturation limit. The saturation limit here will typically stop things from getting concentrations upwards of maybe 10 molar, 15 molar or so. We're typically going to only deal with like 0.5 molar, 1.5 molar, even up to like 3 molar. That's okay. Most of the things are going to be soluble. They're going to be really far away from the saturation limit. We'll come back to the saturation next year. So that was just a reminder of some of the vocabulary in solution chemistry here. We qualify what it meant to be soluble. Let's just step back into the math a little bit here. And let's have a look at our last calculation here, which is a dilution question. So yesterday with our simulation, we were saying, well, because the solid is actually so fully dissolved, you can't actually take a pair of tweezers and actually grab powder that's been dissolved back out. What we can do, however, is we can just add in more solvent. Let's make the pool bigger. The same number of swimmers here in the pool will actually knock my concentration a little bit lower. So for a dilution here, first thing for starters here is you have to already have a solution. So it's like I have orange juice here. Oh, it's already really concentrated here. It's really, really strong tasting. It already has if I look at the formula here, it already has a C1. It already has a starting concentration. C is always given by the number of moles divided by the volume. And I'm just going to put volume 1 here. So that's my orange juice here. It's really, really concentrated. All I'm going to do in a dilution, same thing would happen for evaporation. In this case here is I'm going to add water. I'm just adding the background without actually adding more powder, right? It already is so concentrated. What's going to happen here is I happen to have, let's say, 4 X's. As I add water, the pool itself gets to be a lot bigger. However, you didn't see me sneak in any other chemicals. So whatever moles that I actually had before, so if I had 4 X's before, let me actually label this better here. These X's here actually refer to the moles of particle. These are my number of swimmers. All that's happened is the number of swimmers actually stays the same. We can actually use that to our advantage. During a dilution, the moles remain constant. Exactly the opposite here for evaporation. Evaporation, I'm going to imagine that the water escapes, but it's the moles, the X's that actually stay constant. So what I can do mathematically here is I can just rearrange for N. So N is going to equal to C1 times V1. If you know the starting molarity, the starting taste of this orange juice, and you know the starting volume, after you add water to it and we're finally at a V2, now that we're at a new volume, I know the color intensity is going to be a lot less. I know the taste is going to be a lot less strong as well. This one here will similarly have a C2 and a V2, but if I multiply those two, N is also equal to C2 V2, and we just said the moles remain constant. The N here, I have 4 X's before, I still have 4 X's afterwards. It allows me to make these two equal. For a dilution, you can actually set this up here. C1V1 equals C2V2. So this is going to be our standard dilution formula. I only want you to use this formula for a dilution or a mixing question that we'll see upcoming. So this basically says if I had 4 X's before, I still have 4 X's afterwards. For this formula here, what we're going to want is to have consistent units. Consistent units just means to have the same units on both sides. If this one here happens to be molar, this one should be molar. If this one is milliliters, make this milliliters. If this is liters, make this liters. Just make the units the same on both sides. technically speaking, because the capital M here, that capital M means moles per liter. Realistically, I really should be using liters times moles per liter to actually get to moles, actually get to a counting number of how much chemical there is. However, because we're just setting up a ratio, if you had divided 1,000, I would have multiplied 1,000. It would end up just canceling out anyways. So let me just show you how this dilution question is typically worded. Let's say I'm preparing for a lab here. And what I need is I need to make 250 milliliters of 3 molar HCl. Right. So I want, if I had a full liter, I want there to be 3 moles. I don't have a full liter. I only have a quarter of a liter here. What I'm going to have in the prep room is usually what's called stock HCl. Stock usually has the terminology, this is the original bottle. This is usually the really strong stuff. This is usually the highest concentration or higher concentration than I would need. Stock HCl here happens to be somewhere around 12 molar solution. So this one here is really, really potent. We definitely want to use a fume hood. We definitely want to be careful when we're diluting it. It's going to start getting really hot really quickly. Now I know this concentration here, it's like super concentrated orange juice here. I only need that diluted version of it. I only need 3 molar of it. And in fact, remember for all the solution chemistry calculations, they're usually going to give me 2 numbers. In this case, they also gave me a target volume. I actually only want 250 milliliters of it. So my bottle, maybe when I ordered it, maybe it came to me in a 2.5 liters or 4 liter bottle. I don't need that much 3 molar solution. I just need 250 milliliters. So what I want here is just sort of backtrack. I want to take some amount of volume, right? Start with a little bit of the really strong stuff, a lot of swimmers, right? This is 12 molar. I want to know how much volume. I'm expecting it's going to be less than 250. How much volume do I start off with? So that by the time I've added enough water, remember we don't add water into acid, I would actually just measure the amounts. I would start off the pool of water and then pour my stock inside. Always add acid. Always add acid into water. So that's one thing to keep in mind. But how much would I need so that when the pool has been diluted to a final 250, there are enough swimmers in the 250 to make my concentration labeled as 3 molar. So because we're adding water in this case here, we're definitely going to be doing a dilution. You don't need to show me the derivation. You can go straight C1V1 equals C2V2. It essentially says the moles stay constant. I know the swimmers had to have come from the stock container here. How many swimmers do I need so that by the time I've added enough water, by the time that the pool is 250, the concentration would be 3 molar. So let's try it out here. Well, starting off, it doesn't matter what you call 1 or 2, just make sure you're careful. In this case here, let's call 1 the stock, the really strong stuff. The really strong stuff here is going to be 12 molar. Regardless whether it's in the whole bottle or regardless if I pour it out here, imagine this for orange juice. When you pour it out of the pitcher into the cup, the orange juice in the cup tastes exactly the same. The concentration is intensive. It says, pretend I have a liter. I don't have to have a liter in my stock. I don't have to have a liter in my how much I actually pour out. But pretending I have a liter, it's like I have 12 moles for a given liter. I don't know how much V1 there is. I don't know how much of the strong stock solution I'm going to need. But what I do know is I want to have a 3 molar solution at the end of it, and I want to multiply it by, technically you should say 0.250, just to prove to you here I can use liters, milliliters here, I'm just going to use milliliters, just setting up a ratio. So we can just do a little bit of simple math here. If I go 3 times 250 divided by 12, this gives me here 62.5. So let's backtrack here. What this calculation has said is you're going to start off with 62.5 of the really, really strong HCl. You pour out 62.5, the difference in volume, notice that this 250 here is actually the final volume. I already had 62.5, so how much water do I add? 250 minus 62.5. The language you can say is, I'm going to add it to the 250 mil mark, so I'm going to add about 180 mils, 190 mils or so. By the time I added to 250, there were enough swimmers in the 62.5 to now make this overall pool having been diluted by 4. In fact, sometimes people like taking this formula here. You can actually rearrange it. You can say, well, what's the new concentration? What's the new C2? I would just bring the V2 down here. C2 is basically what C1 used to be, but we're setting up a ratio, C1 times V1 divided by V2. So this is just a slightly manipulated formula, dilution formula. This one here is going to be the new concentration, the new molarity, the new how many moles per liter there are. This one here is the initial concentration. The V1 is actually going to be the initial volume. And just careful here, V2 has to be the final volume. This is the total volume. You notice in this question here, it was not the amount of water I added. I only added 180, 190 or so that I make it up to the mark. So in this case here, just a language, I can say add water up to 250 milliliters. That means I already had the 62.5. Or I can say that here, 250 minus 62.5, I can actually say add water, add 187.5 mils of water. So both of those will end up having a final volume of 250. I'm going to punch in a final volume 250 there. What's actually happened here is this V1 over V2 is actually called a dilution factor. It actually is just a ratio after all. So if you actually looked it up here, if my ratio was I was 62.5 and eventually my final volume is 250, you're going to find that that's actually just a quarter. Oh, of course, the initial concentration was 12 molar. I take a quarter of 12, 3 molar. So if you can just think in terms of ratios here, that might actually help you in trying to figure out what the final molarity is going to be. Finally, we're going to do one last question here. This is a mixing style problem. A mixing is essentially just two dilutions in one. When I'm going to set this up here, we'll just do it by way of example. Let's imagine I have 10 milliliters of 1.5 molar NaCl. So I've already made a solution to begin with. And I'm going to mix it in with another solution here. Let's make it 20 milliliters, so a little bit more volume. These are two totally independent solutions. And let's say this is sodium oxide, right? Two totally different chemicals. Let's use O's to mark them. What I'm going to do is, as the name suggests, I'm going to mix these two solutions together. I'm going to pour the solutions together. Now, literally, you could actually mix one beaker, just drop it directly into the other. Normally, I find picture sake here. Let's imagine I have a third container that's just ready to receive the extra volumes. So at first, you drop in the 10 milliliters. There's your 10 milliliters of the NaCl solution. The other solution here is 20 mils, so that doubles even more volume there. I'm going to ask the easy question first. When I add 10 mils into 20 mils, what's my total volume? We're going to assume that the total volume, right, just 10 plus 20, assume that there's no splashes or any leftover bits here. The total volume here is going to be 30. We have to be under assumption here. As I drop in these X molecules NaCl, as I drop in the other type of swimmers here, I'm going to make an assumption that these chemicals here don't actually react. Assume that there's actually no reaction between the O's and X's. So the swimmers actually don't care there's actually other swimmers present. All they really care is, well, I used to only be in a pool of 10 milliliters, but now the pool is tripled, it's 30. I used to be in a pool of 20. When I get poured in here, it's going to be 30. Now in this question here, I actually left it fairly simple. How can we guarantee that there's no reaction? If you try doing NaCl, you try doing Na2O, although this looks like a double replacement, because Na is the same metal, even if they swap places, it's going to effectively be no change. So what we're going to do here is we're going to do two dilutions in one. Let's do on the left-hand side here, C1V1, C2V2. This is talking about the NaCl. And on the other side, let's do C1V1 equals C2V2. And this one here is talking about the Na2O. The most common problem I see for this section here is people going, oh great, I have a V1 and a C1, I have a V2 and a C2, and they accidentally set these two equal to each other. What I want instead is I actually want the total pool size is actually 30. If the final volume is actually 30 in both of these cases, how low did these concentrations drop to? So let's just work this out here. For this section here, we're always going to do the dilution part first. We'll finish up with the dissociation. My starting concentration was 1.50. My initial volume was 10. I don't know what my new C2 is, but my final volume is 30. That volume ratio would be 10 over 30. I'd imagine it'd be a third. So even if you punch in the numbers here, this one here should give you 0.5. So thinking in fractions there, that should help. So 0.5 molar of the NaCl. On the other side here, similarly, this concentration was 1.20, a little bit less concentrated. Let's take 20 mils. What's the new concentration, assuming that we're 30? And again, thinking as a dilution factor, 20 over 30 would be a ratio of 2 over 3, 2/3 of 1.2. Don't know what the number is, 0.8. And there we go, 0.800 molar, C2. Always do a mental check for yourself. Does this make sense? Well, because the pool is now bigger, 10 became 30, this concentration dropped. Because the pool was 20 here, this concentration doesn't drop by much, but definitely it did come down from the 1.2. So at least that's your mental check. Now again, another common mistake is people go, okay, now I have these two concentrations, do I add them or do I leave them separate? The question here is you need to ask yourself, are these the same chemicals or are they different? Well, NaCl, table salt, is different from Na2O. Now sure, it has sodium in common, but this is almost like comparing apples and oranges. Your final answer can be, here's the apples I have, here's the oranges I have. You don't combine them. What I'm going to end off with here is one last step. Because these ones here are ionic compounds, and alkali salts at that, we can actually refer to a dissociation reaction. We can actually do that breaking up process here, figure out how many ions are actually formed. Because water would have actually separated this lattice, it would have separated the positive from the negative. So if I take NaCl, if I break this up, this becomes 1 Na plus 1 Cl minus, we wrote that earlier. The Na2O, in a similar fashion, it's going to break up to become Na plus and O minus 2, a ratio of 2 there. I now have my concentration of 0.500 molar. This one here is in a 1-to-1 ratio. We're going to do this ratio stuff a lot more in the next coming days here. I always picture this as sort of like a candy. Imagine my recipe says, for one candy, one blue and one red together, every time water chops up this candy, it's going to give you one blue and one red. So that's what this the coefficients tell you. So if I have one of this, I get one whole blue, one whole red. If I have 10 of this, 10 whole blue, 10 whole red. If I have 0.5 of this, I would imagine I get 0.5 of this and 0.5 of this. And although I leave my work like that here, it's understood that this has to be completely gone. All the candies are now ripped apart for me to have the final concentration as 0.5, 0.5, like this. On the other one here, I had my concentration as 0.800. We're going to do the 1-to-2 ratio, so 1.60, 1-to-1 ratio, 0.80, again, assuming that this one here is gone. And now I'm basically done the question here. I want to just list for you what's the concentration of the ions. The chloride came from the first solution. I have 0.500 molar of it. The oxide came from the second solution. This one here is actually 0.800 molar. The sodium is a little bit harder though. Earlier we were saying, well, they're apples and oranges. Why bother add these two chemicals together? In this case here, I actually do get sodium from the left-hand side. I also get sodium from the right-hand side. Long story short, what you're going to do is you're going to add these two numbers. If the first solution gave you 0.500, your next solution gave you 1.60. In total, we actually get 2.10 molar. If you think about that, that actually is really weird math. Imagine my Na plus here were apple juice. My apple juice were 0.5 molar. The other side here, I also get apple juice here. It's really strong apple juice. If you mix these two apple juices together, suddenly I'm saying your final apple juice is stronger than it was before. Wait, that doesn't make sense. Every time you mix solutions together, the total volume goes up. I'd expect the taste to actually go down. What we're actually doing here is, you're totally right, concentrations don't add normally. But what we're actually doing as a simplification, I want you to think, what does add is actually the moles. So if 0.500 molar is the apple juice on the left-hand side, because we're all in this 30 mils together, I can figure out how many swimmers are there in 30 mils. That's sort of the apple juice on the left-hand side. Let's do the apple juice on the right-hand side here. I should have gotten 1.60 molar. The final volume is also 30. Right. This time I'm actually counting literal number of particles. These are the particles on the left-hand side. These are the particles on the right-hand side. They're both sodium. But eventually we want concentration. I would end up dividing the final volume anyways. And seeing as we're all mixed in the same container, we actually see the 30s actually cancel out. And therefore, for this problem and this problem alone, mixing style questions, it's almost like adding two apple juices together and suddenly get even stronger apple juice afterwards. So try out your worksheet for a little bit more practice with this here, and we'll go from there. Thanks, guys.